This lecture is about a topic known as kinetic energy. In an earlier lesson, I divided the way we look at energy into three categories. There's energy that's being stored. We call that potential energy. There's energy that causes motion or change. And then there's energy that causes changes in temperature. In other words, heat exchanges. What we are going to look at today is that second type, the energy of motion. We call the energy of motion kinetic energy. This comes from a Greek word meaning to move. So if an object is moving, then it is capable of doing work and/or work is being done on it. So this is going to relate to our earlier talk about work as well. So if you think back to our study on marbles and ramps, you might remember that we rolled marbles down ramps and hit a target. If the marble was going faster because it had a steeper incline to roll down, it could hit the target and move it farther. Or if the marble is more massive, then it could also move the target farther. Now that target moving, that's something moving and it's being hit by a force, work is being done. So we could say the amount of work that a marble can do depends on two factors, its mass and its speed. Anytime we get a relationship like that, we ought to be able to find an equation. Now, in our previous look at potential or stored energy, I tried to get you to understand that work and energy are essentially equivalent. Where work is being done, there's some kind of energy change. It's either being used to do that work or it's being stored, changed in potential energy. Now, if an object is moving, then it is capable of doing work. It can hit a target and move it. So if work is dependent on mass and speed, it just makes sense that kinetic energy of a moving object is also dependent on mass and speed. So again, if we have a proportionality like this, we ought to be able to find an equation. So the equation is not quite as straightforward as a 1-to-1-to-1 ratio like it was for work. But in fact, the formula has been found to be kinetic energy equals mass times speed squared of the object times 1/2. Or maybe a better way to write it is to say it's mass times speed squared over 2. I think that 1/2 in front, sometimes you see it in fraction form, 1/2. Sometimes you see it as 0.5. I think that throws people off because they think it applies only to the mass. But in fact, the 1/2 is a proportionality constant, and it applies to the entire equation. So I really like the way that it's written at the bottom of the screen better. So let's see what we can do with that formula. Here's an example problem. A 550 kilogram sailboat is cruising at 3 meters per second. What is its kinetic energy? The mass is 550 kilograms and the speed is 3 meters per second, and our formula is shown on the screen. So let's pause the video right here and see if you can calculate the result. What you should find is that kinetic energy is 550 times 3 times 3 divided by 2. That's 2475 as far as the number is concerned. The units would be kilograms times meters squared divided by seconds squared. And you may not recognize that, but that's a Newton meter or a joule. So the units of kinetic energy are the same as the units of potential energy, which are the same as the units of work. It's the joule. The joule does not have a direction. It is a scalar quantity. So kinetic energy and all types of energy for that matter, are scalars. Although it does matter which direction it goes, in some cases you don't really have to indicate it with, say, a degrees, an angle, or anything like that. You can't represent it with a vector arrow. So let's think about this situation. Let's say you're going to throw something like, say, a baseball. If you throw it, you're putting energy into it, you're doing work on it to give it a certain speed. If that ball then hits something else, it can move it, just like the marble going down the ramp. So you do work on the ball, and then the ball is able to do work on something else. Essentially, work and kinetic energy seem to be just interchangeable. Let's say they're equivalent. So if work and kinetic energy are basically the same thing, then let's look at their formulas as being equivalent. So the formula for work is force times distance. The formula for kinetic energy is mv squared over 2. So FD equals 1/2 mv squared. What you see with this equation is a couple of things. First, please note that the speed squared really affects the kinetic energy more than the mass. So if you double the speed, the kinetic energy actually goes up by a factor of 4. But what that means is the amount of work also goes up by a factor of 4. It either takes 4 times the amount of work to cause that doubling of speed, or once it's moving, it can do 4 times as much work. So that speed squared is really super important. Looking again at our 3 categories of energy, potential, and now we're talking about kinetic and heat. I want to remind you that those are our categories as people. Thinking about energy in these different forms helps us to think about what's going on. But in the real world, energy is energy. So it's a very simple matter for one category or type of energy to become another category. Let's take a look at potential becoming kinetic energy, for example. Consider a falling object. If you raise an object up to a height, it now has gravitational potential energy. If you release it, that energy is changed into the energy of motion. In other words, kinetic energy, at least until it comes to a stop. For example, if you take a ball up to 10 meters high and it has a mass of 1 kilogram, you could calculate its potential energy as mass times the acceleration due to gravity times height. If we round the acceleration of gravity off to 10 meters per second squared, then its potential energy would be 100 joules. It is not moving if we're holding it steady at 10 meters high. Without a speed, its kinetic energy would be 0. But as soon as you let go, that ball will start to fall. And what happens is, as it gets lower toward the ground, the amount of potential energy goes down. But what's happening to that potential energy is it's changing into kinetic energy. The ball goes faster and faster. By the time the ball is halfway down at 5 meters high, it's lost half of its potential energy. But if we ignore air resistance, then that 50 joules of potential energy that's, quote, lost has actually changed into kinetic energy. Keeps falling, the conversion keeps happening until it gets right above the ground. When it's right above the ground, its height is 0, so potential energy is 0, but the kinetic energy is entirely taken up now. So if it started out at 100 joules, right before it hits the ground, the kinetic energy is 100 joules. You may have noticed on the earlier slide that it's possible to calculate the speed of the object at any given height, assuming a perfect conversion from potential to kinetic. So let's just do that calculation as an example. How much potential energy does the ball have at 10 meters high relative to the ground, and how fast will the ball be going just as it strikes the ground, assuming that there is no loss of energy to the surroundings. Well, if you read the first problem, you write down the variables that you see. We had a ball that was 1 kilogram in mass, and it's at a height of 10 meters. Sometimes you don't see in the problem the constants, things like acceleration due to gravity. You just have to know them. So the acceleration due to gravity is really 9.8 meters per second squared, but we've been rounding it off just for convenience to 10 meters per second squared. The formula for potential energy is mass times gravity times height. So all you have to do is multiply those three together, and you would get 100 joules, 100 Newton meters. That's how much potential energy the ball has if it has a mass of 1 kilogram and if it is raised to a 10-meter height. Now the second part of the question asks, well, how fast is it going just before it hits the ground? One way to figure that out is to assume that all the potential energy changes into kinetic energy. So just before it strikes the ground, it must have 100 joules of kinetic energy. Now how does that help us? Well, the formula for kinetic energy involves speed, which is the variable we're looking for. So if we take a look at the formula for kinetic energy, we see it's mv squared over 2. Now this is a little bit of complicated mathematics because we need v, not v squared. So what we're going to have to do is multiply both sides by 2, divide both sides by m, and then take the square root. So our formula will end up looking like this. You may want to jot that formula down because it's convenient for these types of problems. But you can always derive it mathematically. So if the speed of the ball must be the square root of 2 times the original, or the total kinetic energy, divided by the object's mass. In this case, that would be 2 times 100 joules divided by 1 kilogram. Now, just for fun, I'd like for you to pause the video here and do this calculation on your calculator to make sure you know how to get a square root. So if you do the calculation, it's the square root of 200. A joule is a Newton meter. A Newton is a kilogram times a meter divided by a second squared. So if you have a kilogram inside that joule there and a kilogram on the bottom, they cancel out, and it's going to leave you with meters squared over second squared. So that should give us meters per second when we take the square root. The square root of 200 is about 14. It's not exactly 14, but that's close enough for our purposes since we don't have very many significant figures here. So just before the ball strikes the ground, it should be going about 14 meters per second if you take it up to 10 meters high and assume there is no air resistance. Again, work and energy seem to be more or less equivalent concepts. So if an object moves, it has or it's using kinetic energy, and to move the object, work must be done on the object. You have to apply force over a distance. If the object is moving, then work is also required to bring it to a stop. So this back and forth between work and kinetic energy is sometimes written as a sort of a simple equation or statement. When an object speeds up or slows down, the change in kinetic energy must be equal to the net work done on the object. It takes work to make it speed up. It takes work to make it slow down. So sometimes you write it into equation form like this. The change in kinetic energy, change in is shown with that Greek delta symbol, it's the Greek letter D, equals the net work. And what we mean by net work is that we are using net forces to figure it out. There can be more than one force. So for example, we often say ignore air resistance. Well, we don't necessarily have to ignore anything if we actually calculate the net work being done. So the net force times the distance moved will give us the net work. So sometimes we call this relationship the work-energy theorem. It's not important to me if you label it as much as you understand what it implies. It takes work to make something speed up. It takes work to make something slow down. If there is no change in the object's energy, kinetic energy, then no work is being done. Now, I shouldn't say it that way because work might be being done, but there's not a net amount of work. Whatever work's being done in one direction could be done in another direction as well. They might cancel each other out. So if there's no change in the object's kinetic energy, if delta KE equals 0, then the net work must equal 0. Example, if you are pushing a box along a floor, if that box doesn't move because it's just stuck to the floor, then you're not doing any work on the box. If there's no distance, then it doesn't matter what the force is, work is 0. If work is 0, then kinetic energy is 0, and that's shown by the fact that the object has no speed, it's not moving. On the other hand, let's say that we had a frictionless floor of some sort, an icy floor. Now any work that we do is going to cause a motion. So any work that you push with will cause the object to pick up speed, and in fact it will accelerate. It'll move faster and faster. If there is some friction, then our net work will be calculated from the net force. So whatever force we're applying in one direction minus whatever force friction is applying in the opposite direction. But once we calculate that net force, now we can use it to calculate the net work. If the box is moving at a constant speed, it is not accelerating. That means there is no net force. If you're pushing against it, but friction's pushing back, you can balance those two and have no net force, there's no net work. So a box moving at a constant speed means that the net work is 0. It doesn't mean that it doesn't have kinetic energy. It means there's no change in kinetic energy when that occurs. So a moving object at a constant speed in a straight line can have kinetic energy, but has a change in kinetic energy of 0. So this work-energy theorem applies both to situations where you make things speed up, like pushing a box, or when you slow them down. So the more kinetic energy something has, that means the more work is going to be required to bring it to a stop. Twice as much kinetic energy means twice as much work, okay? But don't confuse kinetic energy with speed. Kinetic energy depends on two things, mass and the speed squared. So we didn't say if something's going twice as fast. What we've done here is we've already calculated how many joules of kinetic energy something has. We're saying that's how much work is going to be required to bring it to a stop. Because it depends on speed squared, this can get kind of complicated really fast. For example, if you have a car and you're trying to bring it to a stop, if it's moving twice as fast, it's going to require 4 times as much work to bring it to a stop because that speed is squared. If you double the v, then double v is 4 times bigger. I'll show you that in an example here in just a minute. So speaking of cars, they are a good example of how to apply this work-energy theorem. And also, let me show you why it's important to leave a big gap between you and the people around you when you're driving. If you're going 45 kilometers per hour, that's about 26 miles an hour. The typical car with anti-lock brakes today requires about 10 meters to come to a stop once you hit the brakes. That's 33 feet. On the other hand, if you're double that speed, you have now increased the amount of kinetic energy by a factor of 4. And so it requires 4 times the stopping distance. You got the same brakes, you're assuming the same amount of friction with the road, then it just makes sense that all the rest of the energy goes into a further distance to do the work of stopping the same car. So if you're going say 52 miles an hour, then it's going to require over 130 feet to come to a stop. If you double that again and you're going say over 110 miles an hour, it's going to require you over 500 feet, a tenth of a mile, to come to a stop. And that assumes you don't hit anything along the way. So the faster you're going, the more of a gap you have to leave between you and the fella in front of you. If you don't, and they hit the brakes, it's going to require, first of all, a little bit of time for you to recognize that they've hit the brakes, and so you've already lost a little bit of ground right there just because of your reaction time, and that's assuming you're paying attention. So please put the phone down and all your distractions aside when you're driving a 1,000-kilogram vehicle. So anyway, the faster you're going, the more of a gap you have to leave between you and the person in front of you. And if somebody pulls over in front of you and takes up that gap, slow down and give them a gap. It's just safe, folks. It's physics. You can't do anything about it. You can't say, well, my car, is going to somehow come to a stop in a smaller amount of distance. It doesn't work that way. The anti-lock brake is on a car to try to keep it from skidding. But let's say that we somehow lock the brakes and the car skids to a stop. How much farther will the car skid if it's moving 3 times as fast as before? So I don't give a speed here. What you do in situations like this is you either make up a speed and just do the calculation, or you can do it through manipulation of the equation like this. If kinetic energy is mv squared over 2, or 1/2 mv squared, then what we're going to do is we're going to triple that velocity. So instead of putting v squared, let's put 3v in parentheses and square that. That would equal 9v squared. We can take that 9 up front if we want to, but the point is that if you triple the speed, the kinetic energy goes up by a factor of 9. That means that it will take 9 times the amount of work. If you're braking, it's the same brake system, so the same force is being applied. The only way to make up that extra work that's being required is to have a longer distance. Force times distance. If force stays the same, work goes up, then distance has to go up. If the work goes up by a factor of 9, the distance has to go up by a factor of 9. This is what I mean, folks. The faster you're going, the bigger the gap you need to leave, so that if somebody comes to a stop, you have plenty of distance to come to a stop. It's physics. So just to summarize, when something is moving, we say it has kinetic energy. It takes work to get it to move. It takes work to bring it to a stop. Or another way to say that is a moving object can do work on something else in order to come to a stop. So the kinetic energy of a moving object is equal to the work required to bring it up to that speed, or the work that the object can do while going back to 0 miles an hour, coming to a stop. So delta KE equals the net work. We call that the work energy theorem. That wraps up this particular lecture. There is a set of homework problems to do. If you have any questions while you're doing that homework, please contact Dr. Kemp.